to the time-dependent basis. Okay, this is the expansion, and then let's say some notation. Let's write En is omega n h bar, okay, so that we can replace omega n after that. Right. So now when I plug this into the time-dependent Schrodinger equation, okay, let's take the derivative first. Okay. When I take the derivative, it's going to act on this term and this term, right? So times the IH bar here, okay. And I'm still going to use dot for the time derivative. And then I take the derivative with respect to the exponential, which gives me I omega n minus sign. And then a n of t equals to minus I omega n t. And then the whole thing times phi n, and the phi n is time independent. So this is the right hand side. And let's clean this up by saying this is equal to So let's plug in the left-hand side. For the left-hand side, when H naught sees any of these, what's going to happen? Okay, it's not going to do anything to these terms. You move it right here, and it brings down the energy. Okay, so this comes from the first term, okay. And then the second term we can't really do anything to it. So we write it explicitly. Okay. So what comes next? Yeah, somebody else. What comes next? We test this. So let's test this with the eigenbra phi n. Okay. Now what's going to happen to the left hand, to the first line? Okay. Phi n moves right across these functions. Sees this, gives you a delta function. So it picks out, by testing this, you pick out the time dependence, time evolution of the m's coefficient. Right. You're going to get this is the first line. And then for the second line, we're going to pick out the m's eigenenergy. Alright. And then when the psi m tests this, nothing happens, right? Because we can't move that across. Okay. So we get a summation over here. Correct? Okay. So now, once again, let's look at this term, and then if we were to multiply that IH bar inside, I sees I minus I gives you a plus factor. H bar sees omega n gives you En, right? So this term and this over here actually cancels with this. Okay. So what we're left with in the end is that can simply move this time dependence factor across, and then arrive at the differential equation for the m's coefficient. Okay. Is everybody okay with this step? Yeah. So far, no approximations, right? Right? Yeah. Okay. So before we proceed, let's see what this says. Okay. If these were non-zero, okay, meaning that if the perturbation actually has an effect, okay, what happens? As time goes on, okay, the different states are mixed. Okay. Different states are mixed. So this state, the expansion coefficient of this state goes into the time evolution of some other state. So perturbation mixes the states. Okay. And that is quite general regardless of time dependence. Okay. So now we're going to, this is an exact formula. Now we're going to put it in a way that we can do perturbation theory on it. So what do we do in that case? If we want to do perturbation theory, what are the unknowns here? Okay. For a given problem, this is known. Okay, and we're assuming that we have completely solved the original Hamiltonian. Okay, so omega n, phi n, these things are known. Okay, the unknowns are of course the time-dependent expansion coefficients. Okay, these are the unknowns. So what do we do in perturbation theory? Expand the unknowns in the power series. Right? Yeah. So let's introduce a small quantity called gamma. Okay, and we have to attach gamma to this perturbing Hamiltonian. Okay. So let's say that again we have a dial for the strength of the perturbing Hamiltonian. Okay. So let's do expansion for the in terms of the powers of this gamma. So I'm going to have this. Okay, and let's use the usual notation. Zeroth order. Okay. First order. Second order and higher order terms. Okay. So now again we just turn that into a component equation for each power. Okay. What's the zeroth power? On this side we're going to get m0 as a function of c. The time derivative of this is equal to, well, is there anything on the right hand side that's first order? No, right? There's nothing on the left hand side. On the right hand side, it's first order because this perturbing Hamiltonian has order 1. This thing has order 1. And then when I expand this, the lowest order 0 gets promoted to order 1. Right? So this says that this must be equal to 0. So to zeroth order, no change, which is, of course, that's what zeroth order means. Right? So now to first order. The first order and is the most important order. Because if you wanted to do second order with this, it gets too clumsy. There's a better way to do it. But you get some important physics from the first order equation. So to the first order, we're going to get, oh, what does time derivative going to 0 mean? These are constants. So I can say that the m's coefficients are just constant to 0th order. So 0th order equation on the right hand side, I need to have the first order equation. The right hand side means the 0th order coefficient, right? because this has order 1. This is what we're going to work with. Now we're already doing perturbation theory, right? And let's consider a special case. Okay. Consider a special case when we study, well, if we started at time equals to 0, the perturbation turns on. And the original system was in some initial state that was an eigenstate, meaning that meaning that the at time 0, okay, which is equivalent to the 0th order expansion coefficient, I'm saying that the system was in the ith eigenstate. Okay, so I stands for initial. So, right. So in that case, okay, we get to first order the change in the m's expansion, the time rate of change in the m's expansion coefficient is given by, well, this delta is going to remove this summation over here. Okay, and then the AI0 is just 1. So I'm not going to write it out. Sometimes, when you're considering not bound states, okay, you know, this is not equal to if I switch I and M. So how do you remember the order? Of course, if you did the algebra, you know, it leads to this point. But just remember, why do we have M over here? Because we tested with this problem. And why do we have I over here? Because that was the expansion. And then we selected a specific term. Okay. So remember, whatever you test is whatever appears on this side. And so whatever you test must be the brown. Okay. So now that equation is directly integrable. Right? Okay. So formally, this is solved by we can go ahead and evaluate this for some special cases, but let's consider a general case. Okay. What is happening here? Okay, so suppose that the perturbing Hamiltonian, okay, is such that it's equal to some initial perturbation times a function of time. Okay. So this is a rather restricted class of perturbation, but it's very useful. So as time goes on, only the strength of the perturbation changes. The form doesn't change. Let's study this specific case. Then what happens? Okay, we can take the matrix element of this and out. Is that correct? What is this? What election when you hear it? What is this? This is Fourier transform. Except for the limits. So this is not Fourier transform strictly speaking. This is the discrete one, where you have limits, not minus infinity to infinity. Okay. So what the system does is it's going to Fourier transform this thing, the perturbation in the time domain, and look for the component. Okay. The component that matches the energy difference here. Okay. It's going to look at how much it has in that component, and that determines how this evolves in time. Okay.
Should the be
TDPT. Yes, sorry. Okay. So this is the general idea. What the system is doing when we're doing time-dependent perturbation theory is Fourier analyzing your perturbation. Okay. And then it's deciding which energy state you should go to based on the energy content of the signal. So now let's consider an even more special case, the case of sinusoidal or cosinusoidal perturbations. So I'm saying that f of t is equal to I omega t plus e to the minus I omega t. Let's do this. Okay. Nothing changes for the things outside of the integral. And then this is going to multiply by that integral, which is a very elementary integral. Let's give this a shorthand notation. Let's call this omega mi. Okay, meaning the difference between the frequency, okay, which is the difference between the energy, right? Okay, so the integral turns into these should be t prime. Okay. Now everybody knows how to integrate this. You're going to get two sinc functions, right? Okay. And the sinc functions, they pack a lot of information, as you will see. Okay. And this is going to be your first example of what it really means when we say the time energy uncertainty. Okay. So let's go ahead and write out that sinc function. I'm going to skip some steps. Does everybody knows how to integrate this? Right? So when I do this, I'm going to get I omega mi plus omega, right? And then up here, I'm going to get e to the I omega mi plus omega evaluated at t, right, minus 1. Okay. So I'm going to change this term, make a sinc out of it. How do I do it? First of all, I need to factor out 1/2 of the phase up here, right? And then I need some kind of t over 2. Okay. So let's go ahead and work with this term, and then I'll write the second term down here. So this term I can take out a 1/2 of the phase. Okay. And this multiplies to up here. And then from the 1, I'm going to have e to the minus I omega mi plus omega t over 2. Okay. So this is going to give you 2I times sine of omega mi plus omega t over 2. Right? Okay. So this I is going to cancel over here. Okay. And let me put the 2. Okay. Let me put the 2 as so e to the I omega mi plus t over 2. Let me put the 2 down here, okay, which turns into omega mi plus omega, okay, t over 2. So I divided by t, I need to multiply by t on the outside, and then up there is a sign. Alright, and this turns into the same function we wanted, right? So the other one is exactly the same. I'm not going to do the same procedure, right? So this turns into pt over 2. That's the first one. Okay. And then the second one is e to the I minus omega t over 2, and then you have a sinc function omega my minus. And then the whole thing must be multiplied by t, right? Because that's what we took out to get the sinc function. Okay, so multiplied by the whole thing by t. And why don't I emphasize this by writing it here? So we get the result for a sinusoidal perturbation. Okay. So first order we have two sinc functions. Okay. Now what is the physical meaning of this expansion coefficient? Okay. We can relate it. To a probability for transitioning from the initial state to the m cycle state, okay, by taking its magnitude squared. Okay. So let me say that the probability to go from the S state to the M state, okay, as a function of time is going to be given by the magnitude squared of this thing, right? Okay. When we square this, what do we get? Okay. First of all, you get rid of these terms, right? Not exactly, but since they're multiplying sinc functions, okay, the overlap between two sinc functions are small, right, if they're separated. So let's just ignore the cross terms, okay? Right. So if I were to magnitude square this, I get t squared over h bar squared, and then this is called the matrix element, right? Because in the matrix representation, this is a one element. So it's called the matrix element. Okay. And then multiplied by, I'm going to ignore the cross terms, so I just have the two sinc functions, and the phase vector goes away from the magnitude squared. So these are sinc squared, omega mi plus omega t over 2 plus sinc squared omega mi minus omega t over 2. Okay. So this is the probability that I started from the I state, and under the sinusoidal perturbation, I'm going to transition to the M state at time t. Okay. What does this look like? Two peaks, right? So for a small time, okay. Of course, if omega I was here, right? What are the possible omega m's that I will transition to? Right? So the equality to satisfy is, okay, you add omega to omega I, or you subtract one. Right? So this and this, these are both omega, and these are the possible omega m's. Okay. So this omega m is omega minus omega I plus omega. Okay. So that's some information, and this information is, of course, conservation of energy. Right. Now, there's something else. What is the width? What is the width of a sinc function? If I have a sinc of x, which is equal to sine x over x, right? And I say, what is delta x? Right. For this normalized sinc function, what is delta x? It's about pi. Right? Okay. So now when I draw this, I'm going to get the sinc function looks pretty flat, and then over here there's a peak. Okay. So, and the width over here are pi. Okay. As a function of t, how do I determine the width? Right. I say that, let's say this one, so it works more intuitively, you get a plus.
No, the width is not correct, because the horizontal axis is omega.
Right.
So the width should be pi over t or something.
Yeah, exactly. Yeah. So the width over here is not pi. Yeah, I'm sorry. Okay. So, but to determine the width, we can calculate. To determine the width, we calculate omega mi. Let's write it out. Minus omega I minus omega times t over 2. Okay. So I want the magnitude of this thing. Okay. To be less than or equal to pi. Is that correct? Okay. So if I satisfy this, then on the omega axis, I'm within this peak over here. Right? Okay. Yeah, that's right. All right. Okay, so what can we conclude here? We can establish a relationship between the spread in the omega m with the time t. Okay, and let me just copy down my folder. Okay, so I'm going to call this delta omega. Okay, because that is the difference between omega, the real omega m, and the transition, the frequency label over here. Okay, so this is delta omega. So you get that the delta omega is less than or equal to 2 pi over t. Okay? So now we can say that since delta omega is omega m minus omega I minus omega, and this is less than or equal to 2 pi over t, let's put it in the h bar so that this turns into the energy. So we get h bar omega m, which is Em, okay, minus Ei minus h bar omega is less than or equal to 2 pi h bar over t. Okay. Now what does this say? Okay. Let's call this the uncertainty in energy. Okay. And we can say that Em minus Ei is equal to, let's put this over here. Okay, it's less than or equal to, put this over here, we get 2 pi h bar over t plus h bar omega. Let's factor out the term h bar omega. 1 plus. And if I factor h bar omega, it would be 2 pi over omega t here. Okay. So when is this strictly equal to h bar omega? Oh wait, I forgot the plus minus sign. Okay, so I should really say that this is plus minus. So plus minus, plus minus, plus minus. So when is this strictly h bar omega? It will be strictly h bar omega when 2 pi over omega t is much less than 1. What does that mean? After several periods. And so it tells you that although, naively these are two sinc functions, and you say that, well, transition is going to happen here and here. That's only true if enough time has elapsed. Okay. So that's only true. It's only going to go into these states after after several periods. Okay. And it makes sense because if I consider a really short time, does the system know the frequency of the incoming signal? No, right? It takes time to observe the frequency accurately. So that is the real reason for the time energy uncertainty principle. It's just because in quantum mechanics we relate time and we relate frequency and energy as this. Okay. We have this relation. And then because Fourier transform has the uncertainty principle built into it, because you need some time, you need a certain observation time to know definitely what the frequency is. That's why there's energy time uncertainty principle. Okay. So now, this is the short time case. Okay. After several frequencies, after several periods, the transition starts to become very selective. And this sharply peaks over here. But there is a big problem in this transition probability here. Can you see it? What's the big problem here? Oh, no. If you have cosinusoidal, perturbation, we can always go up and down. If I only included one of them, it won't go up. The big problem is t squared term. Okay. Although, actually it's not a problem because you have sinks here. As time gets large, okay, the t squared is actually crushed by the sink function. But this is an ugly expression if we have t squared over here. Imagine what happens if I took time going to infinity, right? The sink would go to delta function, right? But then if I turn these into delta functions, I still have the t squared over here. And at that transition point, at that point of transition, it could be problematic. The probability could well exceed 1. Okay? So this formula only works if you're considering this picture. And it only works at small time. Okay? So for a longer time, although this is still true, but we need to change this just by rearranging the terms, reinterpret this formula for a longer time. So steady state perturbation. Okay. Let's consider, now to make things simpler, because I know that this and this has no difference other than the sign of omega, right? So I can just study one of them for now. The other one is just over here. Everything's the same. Let's consider the perturbation where the time dependence is equal to just this I omega t. Okay? Then I only pick up the this one over here. So in that case, I'm going to get the amplitude to first order is equal to minus I h bar matrix element. And then that integral over here, which turns into a single function. But I'm going to choose, because we're taking steady state. Okay, we would like the history to go all the way back to minus infinity. Okay, so it makes sense to choose a rather symmetric integration interval. Okay, so e to the omega. Okay, everybody okay with this one? Right. Now, what happens when I take the limit as t goes to infinity? Okay, this goes to a delta function, but a 2 pi line times the delta function. Okay, there's a 2 pi line. Okay, so, and I should say this is. And the limit as t goes to infinity, this is minus 2 pi I over h bar. Okay, let's do no changes here. Omega mi plus omega, which translates to omega m minus omega I plus omega, right? Okay. So now if I were to magnitude square this thing, what's the problem? Okay. I get a square of a delta function. Okay. Delta function is only defined when you have what is inside an integral. And if you have a square of a delta function, you need 2 integrals to really make sense. Okay. So that's not good. Okay. So the probability for the I to M transition, okay, this is equal to 4 pi squared over h bar squared by m And then we have two copies of the same delta function. Okay, and should I really say that it's still a function of time as I take the t goes to infinity limit? No. This is no longer a function of big T, because we're reaching a steady state behavior. Okay, so how do we make sense of this? Well, we could change this. Okay, we'll change the product of the delta function into something else. Okay, let's expand one of the delta functions back into here. Okay. So this is saying